So I apologize in advance for my handwriting. I haven't had time to retype this. Okay? And my handwriting is an atrocity. I know. It always has been. Nearly drove my grade 6 teacher to retirement. Okay? But, okay, it's, I think you'll be able to read it enough. If there's something you don't understand there, let me know. All right? So when our lab reports are set up, okay, they're going to go in a certain order. Now, because we're doing this Google Classroom thing this year, you're actually going to get a template for all of your labs. Okay? And in fact, maybe just I'll show you what that template's going to look like here. Okay, so when we do this lab and I assign it, just like we did on Friday there with the Google Classroom stuff, you'll get this file. Okay, it'll be yours to fill in. It'll have your name on it, just like the Google Classroom practice one we did on Friday did. All right, so you'll fill everything in. You'll have a problem, which you will restate in your own words, because the handout I give you will have a problem on it. Okay, then you'll have to tell me what your manipulated, responding, controlled variables are, which I'll explain here in a minute. Okay, you'll write your hypothesis, so you'll just fill in the if part, the and part, and the then part. Okay, you'll leave the materials as it is. I've got a chart here for you to put your observations in. You just have to fill it in. Okay, your analysis, is basically identifying sample A was ionic and or molecular, and it was this stuff. Okay, so that's what you'd have to do there. Right, so you could say sample A was molecular and it was water. Okay, and sample B was ionic and it was sodium chloride, whatever it happens to be. Okay. All right, then you'll have your conclusion, where you'll say, here's my hypothesis, and based on my data and my analysis, I can conclude that these things happened and occurred in the lab, so I can accept my hypothesis or I reject my hypothesis, whichever. Okay, then you'll have your evaluation, where you'll identify your sources of error, usually 3. Okay, anything that gave you trouble, made the lab difficult, whatever was a stumbling block for you, and list a way to improve it. Okay, and then the class discussion stuff, you don't have to write anything for those. They're things that we'll talk about when I hand back the lab, and you'll probably want to just write a few things down in your notes about those class discussion ones when we go over it. Okay, and then there'll be underneath that, the place where when I'm marking your thing, I write in what you got on the design, what you got on the hypothesis, what you got on the procedure. Okay, and there'll be rubrics. Okay, they look kind of like this. Okay, scoring rubrics, right, on your handout that I give you. Right, so you can always compare back to that if you don't understand why you got that mark. All right, does that make sense to everybody? All right, so that filled in is going to be your final product to me. All right, and obviously one of the other things we have to do is the procedure. You have to write out your steps. Okay, and that's what we're going to be working on probably tomorrow. All right. Okay, so when we start out a lab report, we start out with the problem. And the problem is always stated as a question. It's just like Jeopardy. Okay, you won't get it right if you don't phrase it as a question. Okay, so the example here, which would be very simple. What is the effect of light on plant growth? Let's say we're investigating that problem. Okay. So once I have this problem, even before I develop a hypothesis, I should be thinking about what I would need to do to test this. All right? And so what I would probably do is I would think up maybe a way to have a few plants that all got different amounts of sunlight. Would that probably tell me what the effect of sunlight on plant growth is? Right? If I had, let's say, 10 different plants and they all got, let's say we started out with 0 hours of sunlight, 2 hours, 4 hours, 6 hours, and so on until I got one that's got, let's say almost 24 hours of sunlight a day. All right? That would probably tell me over the course of maybe a month or 2 months, what the effect of sunlight is on plant growth. In fact, it might even tell me that, too little is bad and too much is bad. Right? It would probably tell me that. All right, so when I'm designing my experiment, I would have a manipulated variable. Okay, and the manipulated variable is the part of the experiment that I, as the experimenter, either determine or change, during the experiment. All right, so in the case of this, what's the effect of light on plant growth? It would be the light given to plants. Specifically the amount of light, because I, as the experimenter, am varying that. It is variable within the experiment, and I'm the one who's varying it. Does that make sense? What I mean by manipulated? Okay? Manipulated variable is that thing that I, as the experimenter, manipulate, change, or determine a value for the experiment. Okay? The other way to say that would be whatever changes as a result. Okay? Or sorry, that's not right. That's in the wrong spot. Because that got moved somehow. The responding variable, which is supposed to be up there, is whatever changes as a result of what I changed. Okay, so in this experiment, I'm changing the amount of light all the plants receive. What do I hope is going to change as a result of that? What am I watching? The growth of the plants. Okay, the growth of the plants is my responding variable. It's that thing I wanted to test. Okay, I wanted to see what they would do as a result of the change I made. So your responding variable is that thing that responds to the change you made. Okay, in an experiment, how many manipulated variables do you suppose you can have? 1. You can only have one manipulated variable. Okay, here's why. If I do this experiment where I have 10 plants that get different amounts of light, and then I also make every plant get different amounts of water, how am I going to know whether it was the water or the light that caused the change in growth? I cannot. Okay, that's why you can only ever have one manipulated variable. You may have more than one responding variable. It isn't common, but it's possible. Okay, most of the time you have one responding variable that you are watching. Okay. Okay. Then you've got your last type of variable, controlled variables. These are you're going to have more controlled variables than anything else. Okay? Controlled variables are other factors that you need to be A, aware of, and B, controlling. Okay, and hence the word controlled variable. Okay, you have to make sure that they remain the same throughout the experiment because they are the other factors that could also affect the amount of, let's say in this case, plant growth. Okay, they're the other variables that could affect your responding variable. All right, so in an experiment where I'm testing the effect of light on plants, I got to make sure all those plants get the same amount of water. So the amount of water would be a controlled variable. Okay, they need to get the same. They have to have the same amount of soil. They should all be the same kind of plant. Okay, I don't want to have a palm tree, a pea plant, and a radish. Okay, that's changing my manipulated variable. They all have to be the same plant. Okay, they should probably all be the same age. Okay, if possible, the seeds should all come from the same plant. All of those kind of things need to be controlled, so I eliminate any other factors that could contaminate my experiment. All right. The other thing I'd want to make sure of, if I'm testing the effect of light, is that they all get the same kind of light. I don't want half my plants under fluorescent lights and half my plants in sunlight. That's not the same. Okay? That's not keeping and doing a controlled experiment. All right? Does everyone follow me on what controlled variables are? Okay. Usually in a lab report, you're going to identify 3 of those. Okay? 3 controlled variables in a lab report usually. Okay? Often there are more than that, but we kind of keep it to 3. And then you also explain why it needs to be controlled. Right, so like we said here, for this experiment here, the one with the plants, same soil, same amount of water, same temperature, and I would say in there, plants need to have all the same kind of water or the same amount of water, same kind of water, because water is a factor that can affect plant growth. Thus, it must be controlled, or it would interfere with the experiment. Okay, soil. Okay, if they don't all have the same soil, they might all have different access to nutrients, and nutrients help plants grow, and that would interfere with the experiment. Okay, so you would make sure that when you list a variable, here's the effect it would have if it wasn't kept the same. Everybody follow there? Okay. All right. After you do that, then you got to come up with probably the most important part of your experiment. Okay. And that is your hypothesis. All right. A hypothesis is always an if and then statement. Okay? We call it deductive reasoning. That's why we have this if, and then. Okay? We'll talk about that in a second. Okay. So a hypothesis always has the words if, and then for this reason. We want it to tell people what we believe is the relationship between two variables, the manipulating and the responding, or what the possible answer to the problem is, okay, things like that. All right, so it's an if and then statement that communicates what the answer or relationship in the problem is. Okay, the problem I was investigating was what's the effect of sunlight on plant growth. Okay, so in my hypothesis then, I would probably want to say something like, if plants require sunlight in order to carry out photosynthesis and thus grow, okay? And an experiment is performed where 10 plants get varying amounts of time where they're exposed to sunlight, then those plants that receive the most sunlight will show the most growth over a period of 2 months. All right? Does that say what I think the effect of sunlight is? Okay? It says what I'm going to do. Okay? And it says what I predict the results to be. Okay? And that's what a proper hypothesis always does. Okay? The if part tells them what I think is going on. The and part briefly describes the experiment that I'm going to perform. Okay? Because my procedure will describe it in detail. This just describes it briefly. And the then part always tells my predicted results. Okay? If I'm right, this is going to happen. All right, that's what a hypothesis needs to say. All right, and you have to commit to it. Okay, in a hypothesis, you have to be willing to be wrong. Because, quite frankly, in really good science, you're wrong 90% of the time. Okay, most hypotheses cannot be fully accepted when an experiment is over. All right, that's how we learn things. Then you redo it. Okay, you slightly modify it. You make a new hypothesis that's slightly modified, and you try something else. All right, and you keep doing that until you get one that is acceptable. Okay, that's how science moves forward. So it's okay to be wrong. Okay, if your hypothesis, okay, is if and then, and you know, I read it and I go, I know that that's not going to be right. Is that going to affect your mark? It isn't. It's okay if your hypothesis is wrong, as long as in the conclusion you say the data does not support my hypothesis. All right. If in the conclusion you go, my hypothesis is right, no, it's not. Okay, then you're in trouble. Okay, but a hypothesis, as long as it's in the right format, okay, and relates to what's going on, okay, it's okay if it's not going to end up being right at the end. Okay, because in the last year and years before, I always have people, they don't do their hypothesis until they're all done, and then they make one up that's right. It's okay to be wrong. Okay, it's okay to be wrong in your hypothesis. All right, so the example we have here, okay, goes something like this. If plants require light for growth and 5 identical plants are given different amounts of light, then the plants that receive the most light will show the most growth. Okay, pretty simple, but it says what I think is the cause, what I'm going to do, and it puts it out there. So this is what's going to happen. Okay, if my results don't show that, okay, which they probably won't. All right. If I give a plant 24 hours of sunlight a day, it's going to die. All right. In my conclusion, I'm probably going to have to say my hypothesis is not entirely correct. Okay. While to a point, increasing sunlight was good for plants. After this many hours, plants began to show stress and did not grow well. Okay. Something along those lines would be how I would conclude my experiment. Okay, so just breaking this down even a little bit more. Okay, this is what your if, and then should do. If, what the answer or cause of the problem is, and describe the experiment, then what to expect if you're right. All right, now for materials, because this year you're getting this stuff in Google Classroom, you're not going to have to write C sheet because they're going to be on your sheet already. Okay, they're going to be on the one that you're going to fill in with the rest of your stuff. So you don't have to write material C sheet. You don't have to write. Okay, and for procedure, again, that'll be on there if it's a procedure I gave to you. Okay, in the situation that we're going to be working on with this first lab, it's going to be one that you design. So a detailed step-by-step set of directions for preparing and performing the experiment. Okay. and it's got to be kind of cookbook. All right? It's got to go step by step, and you got to assume the person following your directions is a complete and total idiot. Okay? And every single little thing needs to be explained. Okay? It isn't because they are an idiot, but it's because if you don't say every little thing, you can't assume that they read your mind and did these other little things you didn't say. Okay? So your first step when you design an experiment should probably be put on lab apron and safety goggles. Okay? That's preparing for the experiment. All right? You don't want to be liable for someone's injuries should they perform your experiment and not put on safety equipment and get hurt. All right? Because, well, I mean, that's the society we live in, unfortunately. People will sue at the drop of a hat. So make sure that you put in the instructions. Put on this safety equipment. Then you're off the hook. Okay? You told them to. If they chose not to, then it's their fault. Okay? So you'd have that, and then you'd have, really descriptive steps. So if the next thing you want to do after that is get materials, okay, you would say, go to the front table where the, depression plates, scupulas, and whatever else are located, okay, and acquire, one of each. Okay? Then your second step could be perform this test, okay? But don't just write perform this test. By doing this, and make sure you describe how to perform that test. And you also want to tell them what observations they should be making. All right? So when let's say if you're just having a look at the observable physical properties of something. Okay? So if you're looking at all these unknown materials that you've put in this dish, okay, you would probably want to say, well, performing an observable properties test means observing and recording the following things: color, okay, state, texture, okay, is it crystalline or is it waxy, okay, things like that. And make sure you tell them these are the things you need to look for, and these are the things you need to record as your observations. Don't assume that they're going to know what to do. Okay, if you just write perform observable properties test, they're going to go, what's that? Okay, they're not going to know what observable properties. Okay, maybe the person who's doing this, doesn't smell very well or has a cold. Okay, if you don't tell them that one of the important things is to waft the samples and detect an odor, okay, they might not do it because they can't smell anything. Okay, if you write it down, they might get someone to come over and help them. Okay, and say, hey, well, I got a stuffy nose. Can you waft these things for me? Okay, and tell me what they smell like. Okay, something like that. All right. Your observations, okay, charts and graphs, okay, or any other data. So usually in the lab report format that you get from me, it'll say data, okay, and in the data section is where you'll need to either build your charts and fill them in, or sometimes they'll be pre-built for you, like the one I showed you this morning, okay, and all you have to do is put your observations in there. Anecdotal. So A-N-E-C-D-O-T-A-L. Okay? Anecdotal means to basically write kind of, it's not like a story. Story is a bad word, but that's all I can think of right now. Okay? If you were observing plant growth, over a course of 2 months, it's difficult to make a lot of measurements and calculations. Certainly you could measure the height, or you could put the plant on a scale every day and have some of those kind of quantitative observations. But sometimes you also want to write about qualitative things that you see, like plant appeared to be a deeper green. Okay. It seemed to be more leaves or look more full, as opposed to count every single leaf every single day. Okay, things like that, right? Or plant is showing signs of stress and wilting. Okay, things like that. Those would be more anecdotal. They're qualitative observations. They're still things that you see. They're still valid, but they're not measured. Okay. All right. Okay, then your analysis. Okay, in some cases, your analysis will be answering the questions that I put on the lab report. Okay, and other times it'll be identification, or it'll be calculating, or it'll be building a graph and analyzing the graph. Okay, analysis is a very kind of wide concept. Okay, it's different for every lab. How you analyze your data is different depending on what kind of data you have. Okay, so you answer questions. Okay, detailed, explanatory answers. Okay. And obviously, if you had to do calculations, you would show all of those calculations as well. Okay? Sometimes calculations occur in observations, but most of the time they occur in the analysis. Okay? After your analysis, because now you've looked at your data and you've tried to figure out what that data is telling you, okay? Now you need to compare that data to your hypothesis and see, does it support my hypothesis? If it does, then I can accept my hypothesis. If it doesn't agree, okay, then I have to reject my hypothesis. Okay? And you can, partially reject and partially accept a hypothesis. You just have to explain what parts of it were acceptable and what parts weren't. Okay? So you restate your hypothesis. Now, that's super easy for you guys. To restate your hypothesis, you go up to hypothesis and go highlight, copy, and then come down and go paste. Done. Okay? That's all you have to do. It's just copy and paste your hypothesis. Okay? Then explain why you accept or reject it based on your results. Okay? A hypothesis should never sound like this. I was right. Or my hypothesis is good. I'll be the judge of that, thank you. Okay? You better say in there, my hypothesis, which is, here's my hypothesis first off, okay, you just restate it, okay, and then say, this is acceptable because after this analysis or this data said this thing and this showed this or whatever, these things show that, okay, the relationship I predicted was true, okay, therefore my hypothesis is acceptable. It should be a few sentences, all right? It should never be, here's my hypothesis, it's right, all right? Okay, why is it right? How do you know it's right? Okay, what did your analysis say about it? That's what has to go on in the conclusion. All right, so the difference between a 1 out of 4 conclusion, I was right, okay, versus a 4 out of 4 conclusion is detail and explanation and reference to your data and reference to your analysis. All right, and then the last thing, evaluation. You identify your sources of error. Okay, so anything that you found was troublesome. Okay, you're not going to hurt my feelings. In fact, I kind of build sources of error into the labs to see if you can find them. All right, so you tell me, this thing really made the lab difficult. Here's how I would fix it in the future. All right, this thing didn't work very well. Okay, and it made it difficult to get accurate measurements. Okay, something along those lines. The one thing you never want to list, okay, as a source of error is human error. Because I get this all the time, and it makes me so mad. Okay, we forgot to do that part. That was a source of error. We forgot to do this part. Well, then why didn't you go back and do it? Don't say in your sources of error, I didn't do the lab right. That's not a source of error. That's laziness. You refuse to go back and fix it. Okay, don't ever write that as a source of error. Okay, because that takes your whole experiment and it just throws it out the window. Okay, I lost my data, so I didn't have anything. That's not a source of error. That's stupidity. Okay, don't do that. Okay, don't write that in your sources of error. Okay, you never admit in your sources of error that you did something wrong. All right, everything in your sources of error needs to be external things that gave you problems. All right, if I only give you a tiny little amount of something to work with, okay, is that going to make your life easy or difficult? Probably going to make it difficult because you don't have very much. Okay, that could be a source of error. It was very difficult to make observations with small amounts of sample. Okay, if we're doing a lab on plant growth where we've got them sitting in the window, a source of error right now could be it's not sunny outside. Okay, the plants did not get hours and hours of quality sunlight for 3 days while Mother Nature had a fit. Okay, and made it snow in the second week of September. Right? Things like that. Those are sources of error. Okay? They're not your fault. They were completely beyond your control, but they did affect your experiment. That's what goes in sources of error. Okay? I was too lazy to do the experiment right. I didn't listen to Mr. Coderre and didn't follow the instructions and did it wrong. Those are not sources of error. Okay? Those are things you can correct. Okay? You can't correct the fact that plants couldn't get sunlight right now. Okay? That's beyond your control. Everyone may understand the difference? Okay. All right. All right. Now you already saw this is a really bad version of the chart, but that was on the file I showed you a little while ago. Okay. What we're looking for here, okay, in your observations will be things like this chart. Okay, we have samples A, B, C, D. Okay. Here's some of their physical properties like color and texture and whatever. Okay. What were they soluble or not? Did they dissolve easily? Okay. You know, you might want to have a scale for that, maybe 1 to 10. Okay, conductivity is automatically going to be a scale of 1 to 10. Okay, because you're going to have conductivity testers, which I'll show you tomorrow. I'll show you all the equipment you're going to use tomorrow, because that helps when you're putting a procedure together. Okay, to see the things you're going to use. Okay, you'll have pH test as well. Okay, and you'll just be using the little Hydrion papers. Okay, things like that. All right, now the tests that we're going to want to run tomorrow, or sorry, on probably Monday when we get into the lab. Okay, you're going to want to run an observable properties test. Okay, this is why I said don't close your books. You're going to want to run an observable properties test. That'll be the first one you want to run. Okay, why? Because all the other tests will change the sample. All right, this is when the sample is in its pure form for you. All right, so things you probably want to look for: color. Okay, we talked about that this morning being a physical property. Okay, state of matter, is it solid, liquid, or gas? Okay, the nature of the matter, is it crystalline? Is it cloudy? Is it waxy? Is it soft? Is it hard? Okay, things of that nature. Basically anything you can detect with your senses. Okay, odor test, wafting, no taste tests. Okay, remember that. All right, so that's, you'll be able to identify probably a third of the samples with that test. Okay, just by looking at them and being very observant, you'll probably be able to identify about a third of the samples right off the bat. Okay, now you'll want to confirm what they are using the other tests. Sorry, Daniel. Okay, using the other tests. Okay, but you'll have pretty good certainty on about a third. Okay, and then you'll want to perform a solubility test. Now, in a solubility test, it's not just throw it in water and see what happens. Okay, you have to measure a few things when you're doing a solubility test. Yes, you need to check and see if it dissolves. Okay, but you also need to see if the temperature changes. There are a few of the unknowns that you're going to be working with that cause temperature changes when added to water. When you add acids to water, they get hotter. When you add bases to water, they get hotter. Right? When you add some things to water, they actually get colder. How many people have ever used one of those cold packs? Okay, where you pop the little bladder inside that's full of water and then you shake it up and it gets cold. Okay, what's inside of those is ammonium nitrate. Okay, and when ammonium nitrate dissolves in water, it gets really cold. Okay, so something to look for. Okay, we would want to look for color changes as well. Okay, because temperature changes and color changes are indications that, you know, chemical stuff is going on. Okay, and did any odor arise when you added it to water? Were any odors present that weren't present before? Okay, so you can see now, after this solubility test, I can't go back and do any of these tests anymore, can I? Right? It's all, now that it's dissolved in water, I can't go back and say, was it crystalline? I don't remember. Okay, it's too late. All right. Then you'll want to do your conductivity test, which basically just means sticking the conductivity meter in the solution you've created, pressing the button, okay, and recording the number off of the meter. When you're writing up your procedure, would it be important to tell people what kind of water to use, or does it not make any difference? Okay, makes a difference. What kind of water should you use for all these tests? Distilled, because otherwise your conductivity tests are all going to be off, because tap water conducts electricity. Okay, it's got calcium and chlorine and stuff like that, and fluoride in it. Okay, it'll conduct electricity. We want to use distilled water because we know it doesn't. Okay, otherwise it'll interfere with our results. Okay, and we should probably rinse the conductivity tester in between tests. Okay, and you'll get a stirring rod as well. That should probably be rinsed in between solubility tests. All little things. Okay, you can't assume people are going to do these things if you don't write them into your steps. Okay, and then pH test is the last one we want to do. You have to do it last because a pH test is a chemical reaction. Okay, your solution is no longer pure after that test, okay? Because it'll have ions and stuff from the Hydrion paper in it. All right, so it's the one you've got to do last. All right, like I say, tomorrow I'll show you all of that equipment, okay, and then you guys can decide how you want to word your descriptions of all of those steps. Okay. Questions on any of that? All right, so tomorrow is going to be a lot more active day for you. Today was a very passive day for you where I talked and you listened. Okay, some days are like that. But tomorrow and Friday will be you guys working together on some stuff. Okay. All righty, now you're good.